Maybe I can edit some of this crap out. Let's get into this radio. Coffee. Drug of choice. You may have your drug of choice. However, I don't recommend recreational drugs when working on this stuff. Okay, so what we're looking for in this radio is a problem with the VCO going out of lock. A very common problem on these radios. VCOs, especially very wideband VCOs, can be a little touchy. They are, in essence, a servo mechanism system, really. A lot of feedback going on, and there's control voltage filtering to prevent them from becoming unstable. If you want them to find their target frequency quickly and lock up, and once they lock up, you want them to basically go into a slowdown mode where where the control voltage doesn't have a lot of effect on the frequency. So you want them to be stable. Basically, you've heard the term phase noise. Well, phase noise is the shifting the shifting of the frequency back and forth as the system goes back and forth in and out of, well, not in and out of lock, but trying to stay locked. It'll continually hunt within a small range of error. And if it does it quickly enough, you have phase noise. So what we have here is the 4 VCOs, which establish the 4 frequency ranges, establishes the entire 30 kilohertz to 30 megahertz range, is broken up into 4 VCOs here. This, in order to provide mechanical stability and eliminate microphonic modulation of the frequency, they poured glue in here. They literally poured a layer of, I guess, thinned out or liquefied like rubber cement. And rubber cement, in addition to having solvent, some sort of a rubbery compound, whether it's a synthetic or natural rubber, and some solids. And God knows what else they put in it. But what would happen is the glue, over some period of time, would become conductive, and it would be affected by humidity, and it would cause voltage leakage, and the control voltage loop would start to leak, and it would leak enough that the loop would go into its more rapid adjust mode, and it would go out of lock, and it would stay out of lock, or it would pull the frequency so far off because of leakage across the oscillating capacitor that it would go out of lock. Or the Q of the oscillator would drop down so low it would go out of lock. So it would go out of lock for a number of reasons, but all of which were caused by this damned glue that they put in here. Now this one has been cleaned out, but allegedly still has the problem. So this is VCO 5, and it has some issues too. This is this is an interesting oscillator. This is a dual speed oscillator, meaning it has 2 modes. It has a rapid adjust mode where it locks in, and it also is the frequency modulation oscillator. So it has a mode where it really locks in and goes to a very slow speed. In other words, it actually tries to undercorrect so that you can apply audio to it and modulate it, FM modulate it. And if it stayed in the more rapid response mode, it would try to correct that frequency shift due to modulation. And then, of course, the phase lock control circuit would be fighting the audio and you don't want that. So it has 2 modes, and this frequently has a problem. And I see that there's no glue in there, and everything looks fine in there. So let's power up the radio and see what we have. See what we find. So first thing we're going to do is, if there was something wrong with this radio, like something like really broken, like, oh, it's smoked and arced and doesn't work anymore, well then what I would do is a good visual inspection. Before you put power to any radio, you really should give it a very thorough visual inspection. You know, wiggle the boards, make sure the screws are tight, you know, tap it, rattle it, go over it thoroughly visually. Stick your nose in there. Smell things. Whoop, that's not good. Spin the fan. Make sure that was working. That's often an indicator, fan doesn't turn. Maybe we got a finals problem, you know, like that sort of thing. Give it a good visual inspection. It actually pisses people off when I open up a radio and I find something loose and I put it back in, turn it on, and it works, and I put it back together. Okay, bye. You know, never powered it up. All right, this is not right. That's not what I want. Here's what I want. Dummy loads. Always put on a dummy load. At some point we're going to do a video on homemade test equipment apparatus. I have quite a number. I used to have them on my website, but Comcast, our local cable provider, decided that they were no longer going to support user websites, which really pissed me off. Because I didn't get any money back on my bill when they did that, but they took down my website. They took down everybody's website. I consumed all of 17 megabytes of their precious server space and never ever needed their service in any other way or took any of their time. But perhaps that wasn't the case with the other Comcast clients. I don't know. All I know is that they took my website down and I'm not happy about it. And I have yet to find a web provider that I like. So, we're doing a YouTube channel. So we're going to put all this stuff on YouTube. Test equipment. I have a lot of little metal boxes. Here, let me show you one. Here's one. Used to get these at Radio Shack. Remember Radio Shack? This happens to be an RF detector. Very simple. Capacitive input, a 1N34 diode, a choke, and a ferrite bead. DC out. It gives me a positive voltage. You can do them for negative. You can set them up negative voltage. They're a little bit more sensitive. But yeah, simple RF detector. Demodulator, essentially. And you can put a scope probe on that and put that into your scope. So if you have a 15 megahertz scope and you're looking for, you know, 150 megahertz signal, this will demodulate 150 megahertz and give you a DC level on your scope to represent that. Can't see the sine wave, but you're interested in the level, right? And dB is all relative. So even if the level's not accurate, the relative dB is. So, you know, simple stuff. I mean, there's nothing in there. It's like, you know, 20 cents worth of parts. A little bit more complicated is some of my injectors. I have some transformer coupled devices in my RF line where I can inject stuff from my signal generator. I got about 40 dB of isolation. So run my signal generator up an additional 40 dB, and I've got a signal level into the receiver. If I accidentally key my transmitter, I've got 40 dB of attenuation. I'm not going to blow my signal generator up. I can go full 100 watt transmit and not worry about damaging my signal generator. I always use pads on everything. whether it's 6 dB or 10 dB, but it's going to be in that range. I always use pads. Nothing is connected directly. Not my spectrum analyzer, not my signal generator. My scope, yes, but even my scope is going through a 10-to-1 probe. So, I've got at least 9 megohms there of protection. So yeah, always protect everything. Have some sort of resistive, dissipative device between your test equipment and your device under test. Just good procedure. You can always add 10 dB to the numbers. If you can't see the signal and you need to remove that attenuation, you can do so carefully, but don't leave it that way. Okay, so we're all ready here to power up this radio. Okay, and we're going to power up. Well, nothing's happening. That's because I didn't turn the power supply on. Power supply is on. That voltage doesn't look right. Okay. Okay, I did not have a 13.8 because I have a pot that is apparently dealing with a little age-related issue, not unlike your host. Okay, 13.822. Let's power this sucker up. And blink. It momentarily came up and went all dots. The dreaded dots. So it came up with a number, which doesn't mean that it's oscillating at all. It just means that that's what the processor wants it to be at. So we're going to flip it over. And we're going to take our oscilloscope put my oscilloscope at 5 volts per division, DC. I'm using the probe in 10-to-1, and for the initial probing around, it's inconvenient to have the ground lead connected and probing. So what I will often do, I will use the ground on the other lead and just go to chassis ground with that. If that's too noisy, because sometimes you will get noise depending on where you live. If you live close to a radio station or a big city or whatever, sometimes you will get noise on the scope probe if you don't have a ground more local. So I will insulate the clip lead and extend it with another clip lead, and I will ground that. So that gives me more freedom. You want to try to stay neat if you can, and not short things out. Take my little probe off. Now, what I'm going to do is I'm just going to look at the control voltage here and see what the hell it's doing. The control voltage comes in on this yellow lead, and it's the same control voltage for all 4 oscillators, regardless of what frequency I'm at. Normally, I would set on all these digital radios, I would set a memory or a bank of memories to be in the center of each band. This way I could just go click, click, click up and down through the memories and go from band to band to band to band to band. On this radio it has a 1 megahertz button for up down. So I can hit 1 megahertz and it will go up, which is convenient. But for now I'm just going to go probe that 5 volts per division. Not in channel 1. I set my channel 1 to 0. Ground, 0. Look at my noise. Test my probe. There we go. Boy, that's not bad. Am I grounded? Let me show you something. See if you can see this. Alright, I am not grounded. And you see the amount of noise on the scope. Now I'm going to grab the ground. And it's not connected. Going to connect my ground. And now I'm going to grab the ground. Look at that. That's in my other hand. Drop it. Okay, there's my ground. Now, here it is sitting in my dry hand. My hand is dry. Now I'm going to squeeze it. I'm touching it. I'm touching it. It's fully in contact with my hand, but my hand is dry. Look at the variability in that grounding. Isn't that amazing? Okay, dry hand, wet hand. So, yeah. Put my strap on. Okay, I'm just holding the down button at 1 megahertz per division, and I'm going through the bands, just running through it. Alright, I'm seeing nothing. No activity whatsoever. It's not even trying to control the main oscillators. That's a little strange. Let me see what's going on with this little bugger here. Okay, I have, I don't know if you can see this. Remember I said visual inspection. How important that is. What I have found right here, there's a broken wire on this oscillator output. We're going to pull this board out. What fun! We might have to replace this whole cable. Okay, power up. And we're stable. So, that was an easy fix. Now, what did I say before we even opened up this radio? How many? There's a test on Thursdays. Everybody remember? How many problems are usually connections? 95%. Now, that's a problem. We're out of lock when we go to that band. So, as soon as I go above 14.5, I lose lock. And we'll see that. Let's go back to the scope. Now, sometimes I go strictly by the chart. Normally, actually, I do go strictly by the chart or the voltage reference given in the tuning procedure. However, there are instances where the voltages available from the VCO controlled circuitry are not ideal. And so what I will do is I will center the tuning range between the supply rails. Now, what does that mean? If the control circuitry is capable of reliably delivering between 2 and 6 volts, and they want a particular peak voltage to be, you know, 4 to 5.8 or 3 to 5.8, you know, something like that. And I find that it has trouble delivering 5.8 reliably. I'll bring it down because I know I've got a whole volt available between. It just came back on oscillating. I know that I have a whole volt available to me from 3 to 2, so I can bring it down. So I might bring it down to like 2.5 to 5.2 or somewhere. So I'll shift my tuning range to accommodate, you know, more optimal voltage supply capability from the charge pump or the VCO control circuitry. That doesn't always happen, but sometimes you need to do that. Okay? And I'm going to program the following frequencies. And this is going to be the top and the bottom of each oscillator range. So we have 4 oscillators. VCO 4 is actually 4 oscillators. It covers 30 kilohertz to 30 megahertz. So let's start with 30 to 30. Okay, to 30. So clearly we have a problem on that band. So let's start there and we'll work our way down. Oop, upside down. Okay. Now, actually, let's get the other 3 just out of the way so you can see how that's done. I'm going to bring you back to the scope here. And that's my 0 reference that you're seeing there now. And all these other frequencies are the 2.5 to anywhere between 5.3 and 6.3. But 2.5 should be the minimum voltage for all of them. And if I'm not mistaken, these all operate backwards. So if I step through my memories now, starting with 20, yeah, the highest voltage the lowest frequency is the highest voltage. So this higher end of the scale should be 2.5. So this one is clearly too high. So this needs to come down. So 2.5. That's where they want it. We'll go back and we'll look at the other ends. Now I'm going to go past this next one, and again 2.5. Oh, that would explain a few things. Enter. 1, 4, clear. Enter. 1, 4, 9999. Let's try this again. 21. 23. 25. 27. 21. 23. 25. 27. Okay, so there you have it, boys and girls. I finally got it right. 20. Top of the band is 6 volts. All right, 22. Top of that band is 5.2. 24. Top of that band is 6 volts, and finally 26. Top of that band is about 6 volts. Minimum voltage, or highest frequency of oscillation. Remember, these are subtractive mixers. In other words, we're using an oscillator. As we go up the band, our oscillator frequency drops. So the highest frequency of oscillation for each of these, the lowest frequency of oscillation for each of these oscillators uses the lowest voltage, and that is the highest frequency on the display, and that is 21, which is 7.49999, 2.5 volts, which is the set point. Next frequency is 23, which is 14.9999, 2.5 volts, set point. 25, which is 21.9999, 2.5 volts. And finally, 27, which is 30 megahertz, 2.5 volts. And that is the lowest frequency of oscillation for each of these 4 oscillators, and we are done. Alright, VCO 5 is fine. Everything's retuned. I think we're ready to do a quick transmit test, and we're going to do a receive test for sensitivity and button it up. Okay, I have S9 at minus 34 dBm. Subtract another 42 dBm from that, and that's the actual level going in. So at minus 70 something dBm. So that's nominal. It's not. I'm not going to work out the numbers exactly. It's irrelevant. I mean, it's within, you know, plus or minus 6 dB of where it's supposed to be. So I'm not going to worry about it. There's no tuning in this front end that needs to be dealt with. So this radio works. It has been repaired. And we can button this up. That's nice when you know what the problem is. You know the history of the radio. The customer told us exactly what it was doing when it stopped working, what stopped working. We don't have to look for any other issues. Now, if he said we had a lightning storm and I came out and the radio didn't work, then I would be going through every stage of this radio. I would be doing much more critical measurements on receiver and transmit, going through all the bands, everything. But we know that's not the problem. The problem was the oscillator failed. The oscillator ceased to oscillate. We found a broken wire in the VCO. All the VCOs were way out of whack, probably because of a poor connection to begin with. It was somehow distorting the signal or changing the frequency, and it was compensated for by improper tuning, or screwed the tuning up. It skewed the tuning, and so we corrected the broken wire, cleaned up the solder joint, went over the specifications for VCO voltages, assured that they are within range, well within range, and there you go. So now we're going to put our radio back together. Oh. Gotta tuck our wires in here. Don't want any wires pinched in the chassis here. I never liked this one. They just do that. There's really no good place for it. Okay. Not so fast. It's not done yet. Lo and behold, and I lost the audio for this part because I failed to realize my battery failed in my remote mic. But this is after the harnesses were tucked in and screws were in place, we discovered that there was still an intermittent, which had to do with the VCO board, the connections between the IF board and the VCO board. And we didn't discover that until we started moving things around, flipping it over, and that top band didn't want to stay oscillating. So we dug in there and poked around, and I really must apologize to my viewers. You did not get what you paid for, because I had two cameras going in this processor trying to capture everything that should have been captured. I wanted to do an inset on the screen where either the scope or the actual work on the radio would have been simultaneously viewed, and one camera completely failed. I had a bad SD card, and it kept crapping out. It just kept, failing to write. And it turns out I got a bad or a bogus or a counterfeit SD card from Walmart, of all places. So so you basically got half the video, but you got two videos. You got an A and a B, because I had so much boulder dash going on in the beginning that I decided to split it. But that was all, good preface for things yet to come. And remember what I said about connections? Well, there you go. The radio's all done, and you go to put it together, and There's still more connections. The radio was obviously owned by a smoker, which didn't help matters very much. And there was some evidence of apprenticeship in terms of some of the previous service work that was done on it. Screws in the wrong place, or the wrong screws, and missing screws, things like that. Very bad solder, uninsulated connections, wire harnesses not restrained properly. Just amateurish work. So there may yet still be problems to be found in this radio, but for now it all seems to be working nominally, which is good. So there you have it. The next radio on the list is going to be an FT1000 D Mark V. It also was tinkered with. Somebody decided that they wanted to get more power out of the radio, which is always a really bad idea. And they ended up eventually taking the finals out and taking the drivers out. So that's all got to be reset and rebiased, and the ALC and safety circuits all have to be readjusted. And that's not trivial either on these radios now, with the way they're all linked together. So that's coming up, and then we have a 940 that's going to get a complete rework. That's got the problematic solder, so that radio needs to be cleaned up and lots of resoldering done and a complete tune-up, check up from the neck up, so to speak. So more electronics to come. Hopefully we'll get our video and audio issues straightened out so that you have a more robust experience, and we'll get into some reading of schematics and deciphering, or I should say filling in the blanks of what is not in the service manual. Information that is crucial, and how to discern when the service manual is not correct, and that is not uncommon either. So thanks very much for watching, and I hope you enjoyed this, as poorly put together as it was. I can't go back and break the radio and do it over again, unfortunately, but more to come. Thanks again. Bye for now.